Hello, this is how to install and use Linux container LXC, a Linux containerization technology. It uses the various features inside the Linux kernel to provide a very secure version of a chroot. The system that runs inside of the container uses the same kernel space as the host operating system. The official website is linuxcontainers.org. Here in the top menu, there's the LXC element. Let's go to the introduction. We know what Docker is. Docker used to use LXC at its start in the first versions. LXC doesn't need any special patches inside the Linux kernel, uses the features that exist in your Linux kernel. So there's support from kernel namespaces, AppArmor. I am using Kubuntu 24.10, seccomp, cgroups, the version that we have available is version 6. The documentation page for LXC tends to be really old and behind. So in here, for instance, it doesn't say anything about LXC 6.0. Getting started. So I must use on my hardware computer a Linux operating system, which I do. I have a recent enough Linux kernel. And says that on Ubuntu you just install one package. Let's see that. Says apt install LXC. So this instruction is really old. You should use apt, not apt-get. So it will install LXC and the dependencies, including some of the other projects that are hosted at linuxcontainers.org, such as Distro Builder. And LXCFS. Let's continue. LXCFS systemd service, LXC systemd service, LXC net, probably for networking. So we did install, and we should check the configuration. So LXC, most of the executables which are provided by the LXC package have names starting with LXC and a minus. These. So LXC check, config. Let's see what it says. So LXC version 6.0.1, the one that's not yet documented at linuxcontainers.org/LXC. namespaces, kernel namespaces, UTS, IPC, PID, user, network, C group, C group v2 /c/fs/c group. Probably Ubuntu is one of the better supported operating systems, or it was for a while, by LXC. And now we can create containers. We will start by having the user root, create and manage containers, but then there's also the possibility of having unprivileged containers. So your non-root Linux user can do container operations, start them, create them, enter them, delete them, etc. There's a website named images.linuxcontainers.org. Let's see what's available in here. So it says container images for the technologies LXC, or the alternative to LXD, which is called Incos. They are created automatically using this distro builder tool from linuxcontainers.org using Jenkins. We are going to use the LXC template LXC-download, which will ask questions. So let's see the list of available operating systems or container images. Again, the container image does not contain the kernel space, just user space. So there's the Red Hat Enterprise Linux and Fedora family, Alma Linux 8 and 9, Alpine, various versions, the Russian distribution, Amazon, Arch Linux family, CentOS, Debian Ubuntu family, Debian Ubuntu family, Fedora Red Hat Enterprise Linux family, even Gentoo, Linux Mint, NixOS. This one I do not know what it is. OpenSUSE Tumbleweed. This is probably the Oracle Enterprise Linux operating system 7.9.8. Rocky Linux, again from the Red Hat Enterprise Linux family. Slackware, the Ubuntus. And the list ends with Void Linux. What's not available here? So there's Fedora, Ubuntu, Debian, Arch Linux, OpenSUSE Tumbleweed. So at least the 4 major Linux operating system families are present here with various versions. Okay, so we will use the user root to create, delete, manage, run the container instance. And we're at the very first example of actually creating a container. We're using the user root. We're using the template download. So let's see. So there should be a manual page. Says create name template. In here it says that you should use equals after the name. In the example, there's no equal sign. There's support for ZFS, the file system. So let's see. LXC create name download. So it downloads a list of all of the LXC container images that are available here at images.linuxcontainers.org. It's the exact same list that we saw previously. Let's go with Ubuntu. Ubuntu being this guy. So I use Ubuntu 24.10, which is codename Oracular. So that would be this one with AMD 64 CPU. The rootfs is the LXC container image. And it says that the LXC container was created successfully. Apt install OpenSSH server probably inside of the container such that we can connect using OpenSSH. And we can use this alternative when you go LXC create -- template and then download. This again is a command line wizard where it shows you all of the possible Linux images, container images, and then it asks these three questions. The distribution that you want, you go Ubuntu, the release that you want, Oracular, and the architecture, CPU architecture that you want. Or you can not use the template download. But you use a template download. But you specify the answer to the three questions. So Alpine, 3.19, and AMD 64 in this example. The container has been created. Now we can start it. So -n is the short version of -- name. LXC start -n. The command line has returned immediately. Let's see the information. Displays information about the container with the provided name. has a pair of keys and values. The container has a name, hello container, was created from the template Ubuntu Oracular AMD64. The container is running. It has a assigned IPv4 address, also a IPv6 address. Let's see if we can ping this thing. And we can. Let's list information. So the command line is ls. Unlike Docker command line and the Git command line that use porcelans, where you go Docker space and then the verb that you want to run, or Git space and the verb that you want to run. In here, there's a bunch of executables, or starting with LXC minus. So in order to list, you go LXC minus LS. In order to create, you go LXC minus create. In order to start, you go LXC minus start. Minus F equal or minus minus fancy. Column-based output. Let's see it without that. So it just lists the running containers without any details about the containers. So this would be similar to the ls command that just lists names of files. But we want more details similar to ls minus la, for instance. So LXC minus ls minus minus fancy. Whenever you forget the name of the container that you have running, you go LXC minus ls and you'll find out. And we are going to enter this running container, hello container. LXC minus attach. Minus minus name or minus n. And now we're inside the hello container. How do we know we're there? From the bash shell prompt. It says that we're not at AM4, but inside hello container. How else can we see? The same Linux kernel space as the host operating system. But we can see in here hello container. Whereas in here is the computer name of the host operating system. Okay, let's see a process tree. Okay, so we're inside of the container. Some of the minimal executables that we might use at the Linux command line are not available in here. Some are. The image should be a base starting image, should be small, but contain enough functionality, at least for installing additional packages. There's systemd inside. Let's install the process tree executable so that we can look at the tree of running processes. On the host computer, I have installed apt-file, which is a way of looking at all of the packages that are available in the official Ubuntu repositories. And I searched for the deb package that contains this executable /usr/bin/ps3. Says that the name of the deb package is psmisc. Let's see if we can install packages inside of the container. We can see that something is working. It's trying to connect to an IPv6 address of archiveubuntu.com, and it seems to be failing. So there's some DNS resolving, but no networking from what I see. So the networking did not work inside the LXC container instance, and that was because I have just installed LXC on my hardware computer on Kubuntu 24.10, and I need to reboot. So after you install LXC for the first time, the deb package, you should reboot your hardware computer. After restart, I could successfully start the container. You don't actually need to go --name or -n. You can just say the name of the command, such as lxc-start, and then as the unique parameter, the container name, so hello container. The same thing for attaching. I just issue the command line lxc-attach space hello container without any --name or -n. And now pinging inside the container works correctly. Let's see if we can install packages. So apt update. Similar to Docker, when we have created the LXC container instance, a fresh LXC container image of this version of Ubuntu has been downloaded, which means that the deb packages are mostly up to date inside of the container. Usually there's a very short list of packages that needs to be installed if you run the command line apt update followed by the command line apt upgrade. Very often no packages need to be installed. In the few hours after you have created a fresh LXC container instance by actually downloading a fresh LXC container image for that container. Okay, so the command line, the package that we want to install is called psmisc. We want to run the command line ps3. So inside of the container, we have a separate user space, again using the same kernel space as the host operating system. And currently we have only a very short list of processes running inside of the container. We have a PID1 systemd and a cron and a syslog and other systemd processes for networking, for DNS resolving, for the logging. PSAUX shows the same list of processes. So process ID 1, which is this guy, and then the rest of the processes started by PID 1. So a process 3, the root is systemd, these are its children, and then rsyslogd has 3 more children of its own. So pretty clean, but you have systemd. When you have systemd, you're actually inside of a full-blown container, not a process container, but a system container. So there's no problem for you to install in here additional daemons. So you can have a Linux XLC container that's of type pet, not cattle. So you could, for instance, install the OpenSSH server such that you can connect to the LXC container instance in a more standardized way. And then inside you could do a ton of things like installing a LAMP stack, so a Apache HTTP server, a PHP, MySQL, etc. You could do debugging. You could install the Visual Studio Code tools that you run inside of a SSH server, so remotely, for remote debugging, remote programming, etc. Let's actually do that. When we have created the LXC container instance, it also suggested that so it said that a container instance has been created, and you can install inside it the OpenSSH server. So let's do that. It installs Python packages, wget the OpenSSH server. It creates the secrets, so public private key pair, more, 3 different protocols. Okay, let's look now at PS3. I don't see SSHD in here. So maybe it's not this easy to install the OpenSSH server. There is a file /etc/ssh/sshd_config, but the systemd service has not been created from what I see. It's an SSH socket. Okay. Let's see on the host computer. So I was looking at the status of the systemd service SSHD, because on Fedora, after you install the OpenSSH server, you actually need to enable the systemd SSHD unit. But Ubuntu works differently. So I have just installed the package OpenSSH-server. But then in order to be able to connect to the container, I need to use the current configuration of SSH server that's inside of the container. And being Ubuntu, it will prohibit connecting using the user root via the SSH protocol and then using a password. And even so, I don't really know the password of the user root because I'm inside of the container. One of the simplest workarounds here is to create inside of the container, after you install the OpenSSH-server package, to create a administrative user that's not a user root, and that's a sudoer. So that's what I did. I have created a user, so add user administrator inside of the container, asks for a password, and then I saw that fortunately sudo is available inside of the container by default, and I have added the user administrator to the user group sudo. So the command lines to run were apt install OpenSSH-server, and then add user space administrator, and then usermod space -a uppercase G space sudo space administrator. And now, if we look at the list of IPv4 addresses, inside of the container, the current IPv4 address ends with 9, so 10.0.3.9, and we can connect using SSH. So SSH username administrator at, and this IPv4 address 10.0.3.9. Press enter. Says that we did not connect to this computer before. Do we want to trust this SSH server? Yes. And it asks for the password of the user administrator. And we can see that the user administrator is a sudoer, because now we're the user root inside of the container. So we have something extremely similar to a virtual machine, where a minimal installation of Ubuntu 24.10 is installed, in the sense that inside we have systemd, we have a tree of processes, we can install additional deb packages, apt command line is working correctly, apt update, apt upgrade, apt install did work correctly, the package -l lists the packages. The only limitation is that it's not a real virtual machine, it's actually a system style container, and we don't have the clear separation of having a separate virtual hard disk, as in the case of a virtual machine. We don't have a maximum random access memory specified amount. and in general, the processes that run inside of the LXC container, you will use less CPU cycles than a similar KVM, QEMU, virt manager virtual machine. Okay, so we managed to install LXC correctly on the host operating system, but that required a reboot. We managed to create the first container. We managed to start the container and to connect to the container either using LXC-attach, or we can connect using plain SSH protocol. Let's see etc OS release. We did apt update, apt upgrade. We did install packages. Again, the list of packages available inside of the container is minimal. It's the minimal list of the packages that are a common denominator for most of the containers that you might run. Let's look at the list of packages again. The package -L. This thing. Okay, so we have apt, we have the minimum system, we have the shell bash, HTTPS certificates, cron, the Ubuntu Debian family of Linux operating systems default shell, so sh, which is dash. There's dbus. There's a DHCP client, device mapper, ext4 tools, Ethernet, fuse, GNOME GTK introspection, GPG verificator, minimal Unix userland, so grep and xip, init, hostname. I have IP space A for looking at the IPv4 addresses. Ping works correctly. Keyboard layouts. The English US locale. AppArmor. bzip. Capabilities. expat for XML. Fast JSON for JSON. More fuse, more GCC. More glib, GTK. More GPG. ICU for Unicode. LZ4, LZMA. And curses for text user interfaces. I have also installed a ton of packages after I have created the container because I have installed OpenSSH server and that installed around 40 deb packages. As text editors, Nano is not available by default. VI is available, as is common in minimal Unix userlands. OpenSSH client seems to be pre-installed. I have installed PS MISC, ton of Python 3 modules, sed sudo was available by default, systemd was available by default, start easy data, udev, vim. So not just Vim Tiny, but the full-blown text user interface Vim, as far as I can guess. wget was installed as part of the OpenSSH server. And that's it. From here on, you can install packages as you want. Let's explore the file system. So this is the rootfs, was downloaded from images.linuxcontainers.org. Again, is minimal, contains only 300 deb packages. Let's actually see. So the package -l, and then wc-l, to 88 lines. So almost 300 packages are installed right now, and I have installed at least 100 of these. So a really small, minimal container image. Unified/USR. I have created a user which lives at the expected place, the place that you would expect, so /home/administrator. The user root lives home directory is /root as expected. Okay, let's exit the container. You do it as usual with Ctrl D, or as usual with exit. Let's list the containers. LXC-ls, LXC-ls fancy-f. We see that it has 2 IP addresses and it's running. And it's privileged, so it's not unprivileged. In this column it says false for unprivileged. It's not marked to auto start. Let's stop it. LXC start is for starting, stop is for stopping. There's no auto completion. And now if we list the container hello container still exists, but it's stopped. And the way to delete it is LXC-destroy. Again, let's look at the list of executables starting with LXC. We've already used attach to connect to a running container, ls to list containers, start to start the container, stop to stop the container, create to create the container. And at the very start, after we have installed LXC, we have run LXC minus check config. Okay, so to delete, we need this one, destroy. So LXC destroy, the name, force, if it's still running. And probably minus minus name or minus n is not mandatory, so it's optional. The usage is wrong, should have a square parenthesis around minus minus name equals. Okay, and now if we run LXC minus ls, there's nothing to show. In the column auto start, we could see that auto start was off for this container, because containers do not start automatically when the host restarts. And we do that by editing the configuration files for the given container, which live under /var/lib/lxc and the name of the container. Let's actually create a container and look inside of this directory. The first time we have created a container with minus minus template download, and now we're going to specify from the command line the answers to the three questions. So let's go to images.linuxcontainers.org to see the version for Alpine Linux. The example uses 3.19, so 3.19 is available. Let's go with 3.21. Okay, so LXC minus create. My container. Template download. And then the rest of the commands, so minus minus. Rest of the command line parameters, minus minus dist. Alpine. Alpine, just Alpine. Release 3.21. This guy. Actually, this guy. Not this one. This one. What's the column variant? So there's cloud and default. Okay, 3.21 and then Arch AMD64. Let's look at the command line again. LXC minus create, minus minus name my container, minus minus template download, space minus minus, minus minus dist Alpine, minus minus release 3.21, minus minus Arch AMD64. That's it. Okay. We have created an Alpine Linux container. Let's list it. It's stopped. Let's start it. Let's list again. Now it's running, but doesn't have an IPv4 address. And now if we run LXC-ls fancy again, we're going to see that the container was starting and it took a while to actually start. And during that start phase, the DHCP client that runs inside of the container has asked for the DHCP server of LXC or a DHCP lease, and now the container, my container has finished starting, has the correct IPv4 and 6 addresses. We can look at more info, LXC-info. Let's do that. It's showing the same information that's available in LXC-ls-fancy, but in LX-ls is presented as a table. In LXC info, it's presented as a pair, a list of key value pairs. So name my container, name my container, state running, IPv4 address, this one, IPv6 address, this one. And then some statistics about networking. Let's connect to the container, LXC-attach. Maybe bash is not available inside of the container because this shell prompt does not look as the one inside the Ubuntu container image. PS AUX does work in here. So PS is actually a symlink to BusyBox. This is the way the Alpine Linux operating system works. So it uses the Linux kernel, uses Muscle as a C library, not the GNU C library, and most of the Unix minimal userland command lines are actually symlinks to BusyBox, such as PS or LS or which. Okay, let's see. The SH is BusyBox. Okay, so we can see that process ID 431 is /bin/sh, which is the default shell inside Alpine Linux, which is actually BusyBox. Okay, let's do what it says in here. So cat/etc/os release Alpine Linux ID version pretty name home URL and bug report URL. Let's see if the networking works. It does. Let's update the package metadata. APK update. Did work. Let's try to upgrade all of the packages. No packages to install. 29 packages. So maybe just 29 APK packages are installed in this minimal LXC Linux container image. Let's see if there's a VI in here. Yes, it's a BusyBox. So that's why it's suggesting to install the package Vim to have the full Vim available, not just the minimal VI that's part of BusyBox. Okay, Let's exit this container and make sure it's still running, but it doesn't have the auto start enabled. So let's try to enable auto start. Okay, and then we're going to look inside of this directory. So let's do that. mc/var lib and LXC. So inside we have just one container. On the current system, we have installed LXC and just one container. The container name is my container. In here we have the root file system. It's actually not a image. It's actually files and directories. That's interesting. And an AppArmor profile. For better security and for better separation between the container instance and the rest of the operating system and the other LXC containers. And then there's the configuration file. Let's see what it contains. We could have nesting containers. So inside of a LXC container instance, you could install the LXC software and then inside create and run additional LXC containers. So running an LXC container inside of a running LXC container. Okay, so in here it says that we should append LXC minus start minus auto equals 1. Let's do that. I'm going to copy paste not to mess up anything. So now the file ends with lxc.star.auto equals 1. And the supreme test is to restart the hardware computer to make sure that the container has been started. So when you run lxc-ls fancy, it will say that the container is marked to auto start and it's already running. Okay. If we want several of the containers we create to have auto start, we can, whenever we create a LXC container, we can specify that the configuration file, so this file should be created not starting from I know /etc/lxc/ default.conf, but to start from /etc/lxc/autostart.conf, such that the configurations that we want to apply to most of the containers are applied automatically. So you create a configuration file, and then when you go lxc-create, you specify the name of the configuration file template. or we can edit the /etc/lxc/default.conf, and then we don't need to specify when we do lxc-create the alternate configuration file. Let's actually do this. So lxc-stop my container -ls. It's stopped, but it's marked to auto start. Okay, so it's interesting. While it was running, it says that it's not marked to auto start, but if I stop the container now, it says that it's stopped and auto start is enabled. It finished starting and it's still marked as auto start. Okay, good enough for me. So it says that a thing that you might not probably expect is the fact that the DHCP leases will change each time you restart the container, which is actually not great. If you create a container instance, if you bother to create a container instance, if you did not destroy the container, why would the DHCP lease change? Makes no sense to me. So in order to actually make sure that the same IPv4 address will be assigned to the same container while you restart the container, or maybe you restart the host operating system, the hardware computer, what you want to do is to set an fixed IPv4 address. And that's done with what? So this is the documentation, DHCP reservation. So it says that inside /etc/default/lxc.net, we have the possibility of specifying a DHCP configuration file. So let's do that. LXC DHCP config file should be not dnsmask.conf, but something else, this thing, /etc/lxc/dnsmask.conf. So by default, the DHCP server offered by LXC uses the operating system, the host operating system's DNS mask, which is a DHCP and DNS server combination. But we can diverge and not use DNS mask, but use a special configuration just for LXC. So let's do that. So this command is looking at the start of the line, at the end of the line. it's searching for a line that starts with the comment character, the pound sign, and then LXC DHCP conf file, and then anything. And this entire line is replaced with /etc/lxc/dnsmask.conf. Okay, so we switched from the /etc/default dnsmask.conf file to a special one /etc/lxc/dnsmask. And now we're appending a file to this file that actually does not exist yet. As we saw inside of the container, if we run uname -a, it will say that the computer name is my container, so probably the DHCP client inside of the container will provide the computer name, the host name, to the DHCP server when it requests an IPv4 lease, and then DNSMask will see that the hostname my container has this lease for the IPv4 address that ends with 100. Okay, let's look at the configuration file again. DHCP my host equals my container and then an IPv4 address. Says that there's such a thing as LXC DHCP range inside /etc/lxc/dnsmask.conf, whereas this file doesn't exist at all. And then we need to restart the DHCP server probably. So let's do that. LXC -ls -f says that the container is still running, so let's stop it. And we stop all. No, it seems that it doesn't have a command line parameter for stopping all of the containers. Okay, the container still exists, but it's stopped. We're going to restart the LXC net, which is a systemd thing, which I'm not sure if service still exists. It does. Okay. So LXCnet is indeed a systemd service, and maybe service is an executable that's provided by systemd for compatibility reasons. We can actually see that. apt-file search, then this thing. And it's init system helpers. Okay. We'll have restarted the LXCnet systemctl service. says that it has started 8 seconds ago. We can see how the DNS mask service is starting as a DHCP server. The IPv4 address is 10.0.3 and then from 2 to 254. So .1 and .255 are reserved. And 255 is a host address, net mask, whatever that thing. Okay, looks okay. And now if we start the container, LXC-start my container, we wait for it to start. And indeed, it has allocated the IPv4 address that we would expect to the container, so the one ending with .100. Which we can see in here that the DHCP server that's inside LXC-net, that's actually DNS mask, has offered a DHCP lease for the .100 IPv4 address. Okay, similar to Docker containers, you might want to have persistent storage. So storage that's not inside the rootfs. As you saw, the rootfs does not seem to be a fuse ZFS overlay file system thing, but it might be. LXCFS. So there is something going on. Use LXCFS. I'm not sure what the rootfs is on the hard disk. Inside /var/lib/lxc/mycontainer/root file system. But we saw that it's read-write because we could install 100 deb packages on the Ubuntu container instance. So it's persistent in the sense that if you don't destroy the container, your changes will still be available in here in /var/lib/lxc/mycontainer/rootfs. But once you destroy the container, this entire directory will be deleted /var/lib/lxc/mycontainer with the entire rootfs inside. So you might want to have storage that persists between destructions of the container. And if you're using the LXC container similar to a Docker container, so if you don't want to do system container but an application container, to have just one application running inside the LXC container, and then you're recreating the LXC container, I don't know, maybe weekly, in order to start from a fresh LXC container image that has all of the security updates applied, all of the binary packages updated automatically by just downloading the LXC container image. Then you probably want a storage that's persistent and that's not part of /var/lib/lxc. So we're using LXC privileged containers, which means that we're editing, creating destroying, starting, connecting to the LXC container instance using the root Linux user on the host operating system. I went to the home directory of the user root, which is /root on the host operating system. In here, I'm going to create a directory. Like this. And then we have multiple options of adding the container, the directory /root/my container workdir to the container as persistent storage. One is to run inside the container the command line make dir with all of the needed subdirectories, so -p, and then the directory inside of the container, and then we are going to edit the configuration file of the my container. Or we could just edit the configuration file with an additional parameter, which is this guy, create equals dir, which is what we're going to do. But for this, we want to actually edit the command line. So let's see. lxc.mount.entry /host/path to volume is this guy, /root, and this thing, /root/my container workdir. And then inside of the container, we'll have just workdir. It says that we should not have a leading / character for the directory that exists inside of the container. So not /workdir, but just workdir. Okay, then none, bind, create dir 00, the correct file, var lib LXC my container config. So this command line seems to be okay. And we want to restart the container. It's already running. We're stopping it and starting it. Wait a bit. And we should be good to go. So we want to test from bidirectional communication between the host and the container via this file. So let's do that. So what do we do? Emacs /root container directory messages.txt. Okay, now we're going to look inside the container. The file is under / and it's named workdir. So cat /workdir and then the messages file. Okay, and we can write some text inside this file. So vi/workdir messages. How do we do that? Message from container. Okay, that's so the container does see the text written from the host and from the container. And on the host, I need to be root. Inside the container, the mount executable sees this thing as the NVMe, so the partition inside the host operating system mounted to /workdir. Okay. The thing that remains is to see how you can create unprivileged containers. All of the containers that we have created right now are of type unprivileged equals false. So they require the user root to be the user that configures, downloads, installs, destroys, start-stops, attaches to a LXC container. So the Linux user root from the host operating system. Or if you're doing LXC inside LXC, then inside the previous LXC instance running container. Okay, so there's a bit of gymnastics going on with user ID and group ID maps. Separate UID and group ID ranges. Common operations that are not allowed if you're not a user root. Mounting file systems, creating device nodes, operation against a UID group ID outside the map set. The recommended way of using LXC containers is to use unprivileged containers. If you're going to be a hosting provider that will run containers on behalf of your customers, you want the maximum security and isolation for each of the containers as possible. So in this case, for sure, you're going to use unprivileged containers. But for my desktop user case, where I might try different things in medium-term lived Linux LXC containers. So for instance, I might do development or connect via OpenSSH. There's no problem for me to actually run the containers as the user root, because only I use my desktop computer. I don't fear any security escalations. So for me, what I know currently about LXC is enough. I can do all of the things that I can think of using LXC container technology. When using unprivileged containers, you are probably using a systemd host Linux operating system, and that will require this dance where you delegate a empty C group to the LXC container using a command line like this, where you go systemd run, and then you go delegate yes, and then LXC starts. So before starting the container, you need to pass inside of the container this delegated empty C group. C group 2. Okay. Then there's additional documentation that you might want to read. There's the man pages for the various LXC commands. There's additional documentation on the major Linux operating system families. Some of these have wiki pages related to LXC. Not all of the documentation is really up to date. C group v1, I'm not sure if this thing even exists. LXC version 4 you're probably not going to use. Debian package 402 you're probably not going to use. And then again, at the very start, the Docker project did use LXC for the first versions. Now it's not using it. And then a technology that's really similar to LXC is LXD/Incus. As far as I know, both LXC and Incus use these images from https://images.linuxcontainers.org, and LXD also used to use these images. Also, in an interesting way, the LXC Incus is written in the Go programming language as a single executable, and the name of the executable is LXC, not LXD. There's libraries. With similar functionality to the executables named LXC-. And that's it. The LXC project has been around for more than 10 years. It's an established technology actively developed by the linuxcontainers.org organization, available in most Linux operating systems, does have an up-to-date, continuously built repository of container images. You might want to actually look at LXC if you need containers in Linux. Yes, there are other alternatives in Linux. There's Virtuoso, there's OpenVZ, there's vServer, there's Docker, all of the Docker-like projects and runners. But still LXC is here, and from what it looks like, it will be available for a while. It uses vanilla technologies that are available in the Linux kernel. No need to use a patched Linux operating system kernel. the kernel, for instance, that's available in the Ubuntu Linux operating system is enough for the needs of the LXC software. So this is it. This is how to install LXC and how to use, how to create containers. Thank you.